Good morning. Thanks very much. And so we'll start the session right away. Please keep in mind that we have 15 minutes for each paper, 12 minutes for the presentation, and 3 minutes for Q&A. So without further ado, we'll start with a presentation by Rowan Thacker. And Rowan, please, can you start?
Yeah.
Excellent. Can you guys see my screen?
Perfect.
Great. Hello everyone. I'm Rohan Thakur. I'm a robotics technologist at NASA JPL, and I'll be presenting our work on autonomous off-road navigation over extreme terrains with perceptually challenging conditions. This work was done as a part of the DARPA Subterranean Challenge with Team CoStar. For people who are not familiar with the DARPA Sub-T, the objective of this challenge was to basically create a distributed SLAM of these subterranean environments like tunnel, urban, and cave. And as a part of our multi-robot solution, a critical challenge is to actually traverse these extreme terrains. And today I'll be talking about how we addressed this navigation challenge. And to summarize, I'll start off by just highlighting a few key aspects of the problem, which make this very challenging. So we have to go over these terrains as you see in the image, which include a lot of mud. There are steep slopes, as well as negative obstacles and dust. This dust in particular can also be very problematic to the sensors which are on board the robot. We have a lot of clutter, and then in addition to that, we have to deal with stairs when it comes to the urban environments like subways. Another dimension of the challenge is perceptual degradation. So these are a few images that are taken from the robot itself. As you can see, it's completely dark, so we have to rely on active lighting. And under these conditions, if we rely on sensors, vision-based sensors, there can be a lot of issues with shadows, which can create false features. Sorry, was there a question?
No.
Okay. So when it comes to these dark environments, there could be issues with shadows, and there can be false features that get detected by visual inertial odometry algorithms. When it comes to LiDAR, which is the obvious sort of solution to robustness, if you notice, we have these cylindrical tunnels. Another sort of challenge is when you are using a LiDAR in a perfect cylinder, the state along the axis of the cylinder, if you're trying to estimate the position, becomes unobservable. And this was actually an issue that we experienced during the tunnel circuit of the challenge. So to summarize, under these perceptual degradation, the kind of estimates that we get from visual inertial odometry or LiDAR inertial odometry algorithms have these failure modes. These can include gaps where the robot just stops, publishing estimates because the entire front end failed. There could be a divergence if you are not able to catch any of these failures in things like ransack of the algorithm, or there could be jumps if you have very noisy measurement updates in the filter. So of course, these issues will then propagate from the state estimate into the map, and from the map into our planner. So a big part of our problem was to kind of deal with these perceptually degraded conditions and still continue operations. And finally, the challenge 3 of our problem included the fact that everything has to run in real time and on board. So in addition to the all onboard constraints, we also have heterogeneity in the mobility platforms. So we have skid steer vehicle, Ackerman drive, tracked vehicle, as well as legged systems. So now I'll talk about how we address this issue. First, so the first line of attack, I briefly talked about this, is to not rely on a single modality, but to shift to multiple modalities like LiDAR, thermal, RGB cameras, radar, and further add redundancy by pointing these sensors in different directions. We have another paper on this, which is there at the bottom of the slide, which goes into the details of how we handle the multimodal estimation under these faults. But what, in spite of all the efforts on the perception end, we still experience those kind of state estimation issues that I showed in the previous slides. So the next step is to actually rely on a multi-fidelity map, which would basically consolidate the pose estimates and depth measurements into a sort of like occupancy grid or a moving window scan that can be used by a traversability estimation algorithm, which I'll talk about in the next slide. And these can be used by different layers of our planner, like the long range planner, mid range planner, and short range planner, with varying levels of fidelity. And then finally, we have another layer, which is independently monitoring the health of the system and triggering recovery behaviors. So now I'll talk about the key contribution of this work, which is about how do we estimate the traversability of the system. So we do make a quasi-static assumption for this analysis. And the problem is that we get a query point where we are trying to assess whether if we settle the robot at this query point, is it going to be stable or will it topple? And to kind of solve the settling problem, what we do is we start by estimating the surface normal of the ground. And once we have the normal, we can then approximate the robot with a bounding box. And then we estimate whether there are any points within the bounding box and if the surface normal satisfies any roll and pitch constraints. So you can imagine if there is a very large slope, we can detect that this is not traversable by monitoring the tilt angle of the settled pose of the robot. And if there is any wall, we should be able to detect a wall by seeing that, hey, there are some points inside the bounding box of the robot. And here are a few other papers that use these related ideas, including the March 2020 rover, driving on point clouds paper, as well as the follow-on work of this that we used in the final challenge for SUPT called STEP. So in the previous slide, I said that basically if we had a map of the environment, we can settle the robot and estimate the traversability. But the big open question even now is how do we construct a map if we don't have localization or if we have these kind of failures in localization? And that's what we'll talk about in the slide. So let's say that, I'm trying to represent the trajectory that I'm getting from any odometry algorithm in some map frame. And as the robot is traversing in the terrain, the uncertainty of the estimate of the position of the robot will keep on growing with distance. So as we traverse more and more into these mines over hundreds of kilometers, our localization uncertainty is going to build up. So the idea is that instead of representing the trajectory in some map frame, why don't we represent the same trajectory in the robot frame or the body frame of the robot? And if we represent the same trajectory in the robot frame, this is how it would look like. The uncertainty ellipses have different characteristics. So for example, if the current location of the robot in the robot frame is just going to be 0, 0, 0. It's going to be at the origin, which is why there will be zero uncertainty associated with that pose estimate. And if I'm trying to look at the pose estimate of the robot, when I had the previous scan at time t-1, assuming the robot is currently at time t, at t-1, the uncertainty will be slightly higher. At t-2, it will keep on growing. So I can sort of like grow these uncertainty ellipses towards the starting point. And that's the key idea that we leverage to get resiliency to these kind of failures from perception. So once we represent our trajectory in the robot frame, we can then use our instantaneous or the most recent single scan. And if we are doing settling on the single scan, then we don't actually need any localization. The main challenge is going to be sparsity. Because you're only using one scan, you will get very few points on the robot. So the next solution, if you want more coverage, is to look at a moving window of K scans, which is what we do for the mid-resolution cost map. And then finally, if we want even more coverage, of course, this is going to come at the cost of higher noise. And that's why we call this low resolution map. And that's the key idea, that we kind of work with these three fidelities and balance the trade-off of noise versus coverage or density of points. So using this trick, we were actually able to deploy the robots into the mines and achieve like traversal over multiple kilometers. And we actually finished in first place at the urban circuit and second place in the tunnel circuit of the DARPA Subterranean Challenge. And our software is implemented in C++. We do use ROS as the middleware and the move-based framework in our implementation. And here are a few results of the robot. And I'm also happy to take questions while we admire the Husky robot traversing through these challenging mines and caves. Thank you.
So are there any questions from here or from the remote participants?
Yes. There's one there.
Hey, yes, thank you very much for the nice talk. My question is, what are your update rates for the different fidelity levels of the map?
That's a good question. So the update rate for the lowermost scan is going to be at 10 Hertz, which is what we get from the Velodyne. And the moving window scan is also running at 10 Hertz. And finally, the occupancy grid is running at around 1 to 2 Hertz.
All right, thank you.
Yep.
Are there more questions? Okay, actually I have a more generic question. So what were the lessons learned from these deployments? Or let's say, if I put it in another way, if you were to start again, what would you change?
So I think like the biggest lessons that we learned in this challenge, I would say, is integration. I feel like a lot of effort has gone into robotics to think about different subsystems of the problem. And I think we are at a point where, we can get the performance level pretty well to solve like 90% of the cases or 95% of the cases. But when we go into the field, our assumptions that we make while developing these algorithms don't generally hold, and there's always this Murphy's law. If there's something that can go wrong, it will go wrong. And that's something that we got a good taste of during this challenge. And another aspect the point I was trying to make earlier with the subsystems is, it's all about how a particular sort of like failure propagates into the entire stack. So we kind of had this, common knowledge of assuming, okay, when I'm doing traversability or motion planning, I'm going to have like perfect state estimation from the perception team. But there are always these tails when those like 1% of the cases when things go wrong, where things generally break. So
Right.
a big sort of secret sauce was to test immediately with the entire stack, and to also like develop the kind of algorithms that look at the holistic problem of all this perception, planning, and control coming together.
Right. Okay. Thanks very much. So I think this was the last question. Now, thank you very much. And next, we switch to the next talk, which will be delivered by Stuart Eifert. I hope that my pronunciation was okay.
Okay, where is the...
Stuart, are you...
I can't see him. He's not. Stuart Eifert. Wow. Yeah, he must have forgotten. I don't know.
Yeah, we just wait for a little bit.
We move it? Okay. And maybe I'll send him an email meanwhile. Okay.
Okay, so the decision is to move to the next talk. This will be done in person by... Okay, my pronunciation will be pretty bad. Okay. Oh, money. Okay, so it's here, and...
You can commute.
yeah,
This one, yes.
okay.
And meanwhile, I'll try to send an email to Stuart.
Yeah, and while he sets up his presentation, basically we'll send an email to Stuart, and if he's around, probably he'll present by the end of the presentation. Okay, thanks very much. So the floor is yours.
So, hello everyone, and thank you very much for attending this presentation. So my name is Othman Wabi. I am a PhD student at the International Research Lab, Georgia Tech, CNRS. And in the next couple of minutes, I will present you our work on Monte Carlo localization on metal plates based on ultrasonic guided waves, which is also work supported by the European Commission. So our research aims at supporting the emergence of the long-range inspection of ship hulls and storage tanks with mobile robots. Indeed, such an application holds tremendous potential to make the inspection of large metal structures much faster, much more reliable, and much more efficient comparing to traditional inspection methods that involve human operators in suboptimal conditions, as you can see on the right figure. So to achieve the long-range inspection of materials, it is common to rely on ultrasonic guided waves, which are also called LAM waves. So these waves can be excited inside materials using piezoelectric transistors. They also have the particularity to propagate over long distances inside the material. And what makes them appealing is that they are sensitive to the material integrity. And this is for that reason that such guided waves are deployed on static network of sensors for the inspection of structures. However, the deployment of guided wave-based methods for the inspection of structures on mobile robots has not yet been established. So to enable the inspection of large structures with a mobile robot, one key requirement is the accurate localization of the robot on a large structure. Because first of all, robot localization is typically required in applications that involve mobile robots, such as mapping or planning, but also in the context of inspection, it is actually critical to know the position of the sensors. And in the case of static sensors, these positions are measured beforehand, and these positions are subsequently used by imaging algorithm in order to detect defects. So in the case of the mobile robot, we will need to accurately estimate the position of the sensor if we want to have, in the next step, accurate inspection results. And this is for that reason that we propose an approach to achieve localization. And the specificity of our approach is that it leverages the ultrasonic reflection on the edges of a metal plate. And also, we are relying on a particle filter, which is quite a common approach for doing some localization. And the performance of our approach is then validated experimentally. So let me give you some more details on how we specify the problem. And the specification is actually not that difficult because we only aim at estimating the position of the sensor and also the orientation of the robot in a two-dimensional space from acoustic measurements that are obtained in pulse echo, which means that the emitter of the waves and the receiver of the waves are located at the same position. And also, of course, we rely on odometry data. So in our case study, we will assume that the plate is rectangular, and this hypothesis is actually pretty realistic because this is the kind of geometries that you will have on large structures, as you can see on the right picture. And we also assume that the size of the plate is known, as we are just in the first place tackling the localization problem. The problem is how to leverage the ultrasonic measurements, how to integrate them inside a particle filter. And actually, this is not as trivial because the acoustic signal can be quite complicated. They contain multiple reflections, and some traditional methods will try to detect individual echoes inside the measurement, but this may not be really efficient because it will be also necessary to identify which reflection, each echo in the measurement originates from a reflection on which edge, and also whether or not it's a first order or high order reflection. So this method they're not really efficient in the case of ultrasonic measurement. So the problem is to find an appropriate observation model that we can use in the particle filter. And it is in that respect that the contribution of our work is the most important. So we actually propose what I will call a correlation-based observation model. And the principle the idea is first to rely on a wave propagation model. So with this propagation model, we are able to predict what the excitation signal will look like for any given propagation distance. And this propagation model is constructed based on assumption on the material and also based on prior knowledge of which material we are inspecting. So with this propagation model, we are able to calculate what I will call a correlation signal from acoustic measurements. So the correlation signal is calculated by correlating the acoustic measurement with all the theoretical signals that are obtained for a wide range of propagation distances. And if we consider the envelope of the correlation signal, as you can see on the bottom right plot, the envelope of the correlation signal will highlight the local maxima of the envelope of the correlation signal will highlight what are the distances from the transducer for which it is likely to have a reflection. And this is this envelope signal that we use in the observation model. So in the observation model, we actually evaluate the envelope signal for all the ranges or the expected ranges that correspond to first order reflections. And the idea is that the probability that is displayed here will be high if indeed there are these first order reflections are present inside the measurement. So to validate the performance, the validity of this approach, we just acquired some acoustic measurement on an aluminum plate. So the acoustic measurements are acquired manually. So we just placed the sensors on different positions on a regular grid on the plate. And also, in order to simulate a robot trajectory, we use the displacement between observation points as odometry data. So here is a small animation of that shows the performance of the approach of the particle filter. So you can see that only after, like at the beginning, we didn't know where was the sensors, which were represented by the red point. But after a few measurement steps, the particles converge to the right position of the sensor. And also, if we take the median value over the particle coordinates, we actually have a quite accurate estimate of the coordinates of the sensor, the real coordinates of the sensor. And the curves here show that we are actually able to have, the estimation error is less than 1 centimeter, which is quite interesting. So this first experiment demonstrated the feasibility of relying on ultrasonic guided waves to achieve robot localization. And in our setup, it was possible to achieve a sub-centimeter precision, which is interesting. But of course, there are many limitations of our approach and our demonstration here. Like first of all, we assume that we know beforehand the size of the plate. We also have quite some assumptions on the material, and some we have some assumptions, and we also assume that we know how the waves behave inside the material, so which might not always be realistic for a practical inspection task. Another limitation is that the experimental demonstration was done on a metal plate that was quite small, and the plate was also isolated, whereas on a real metal structure, you will have several metal plates that are welded all together. So I wanted to take some time in order to show you like the work that was conducted since the work that we put in the ISER paper. So first of all, we were interested in tackling the simultaneous localization and mapping problem. So now the idea is now that we are able to estimate simultaneously both the trajectory of the sensors and also to estimate the size of the plate. And if you're interested, you will find more details in our ROL paper. Another thing we were interested in is how we could integrate the ultrasonic signals within the occupancy grid framework. Well, we actually showed that it can be interesting to do so because, first of all, we can more reliably detect the boundaries of a metal plate. We also this can also lead to more stable plate geometry estimates, despite the fact that the acoustic measurements are very noisy. And it's always interesting to have an occupancy grid because this can be used for a subsequent active sensing or exploration task. And also you can see that we validated this time the feasibility of the approach with a real robotic platform, as you can see on the animation. And sorry for the viewpoint of the video, which is not optimal. Another thing we were interested in is how to automatically calibrate the propagation model. Because assuming that we know how the wave propagates inside the material beforehand is actually quite a limiting assumption. So here it's just a small animation. So here we were able to design a cost that is function of the propagation model parameters. And we show that if we minimize this cost, we can find propagation model parameters that lead to very accurate localization results. So here we are able to accurately localize the plate boundaries from acoustic measurement. And this, I think, is an interesting result for also future practical inspection operation with a robot. And finally, I also wanted to show something that it's actually still very, it's still very at the beginning, but I wanted to show something about defect detection. So now let's assume that we are able to localize, we have good localization, we have good mapping results, that we have a good propagation model. So the idea is that once we have all of that, we are able to predict where are the wave packets inside the signal, as you can see on the left, sorry. And the idea is that, first of all, we use a dynamic time warping algorithm in order to realign the predicted wave packet with the measurement. And after the realignment step, we can remove the wave packet from the measurement. And the idea is that if we remove the wave packets that are due to the reflection, then theoretically the resulting signal will only contain some wave packets that are due to a defect. And we just, here is just a small video that in that case we have real acoustic measurement, but we simulated a defect by just adding a very tiny wave packet that would be due to a defect. And here you can see on the right that after removing the echoes due to reflection on plate boundaries, you can kind of see where is the location of the defect that we simulated. So I think that is still that's still the beginning. It's maybe a bit speculative, but this is something that we would like to push forward to be able to achieve an inspection task with mobile robots in the future. So thank you very much for your attention. I hope you find it interesting, and I am open to any question.
Thank you very much. So are there any questions? I think we still have time for one or two quick questions. Okay, there's one here.
So, very nice work. I wonder, in the most recent thing that you have shown, the SLAM algorithm, are you like introducing, the number one? Are you introducing any hypothesis on the environment be a rectangle?
So on the SLAM algorithm, I'm assuming that the only assumption actually on the shape is that we have a rectangular shape. So yeah, that's an hypothesis on the geometry, but there's also a hypothesis on the way the wave behave inside the material. For example, we make the assumptions that the wave propagates the same way, and this does not depend on the direction of propagation. So we also have a hypothesis on the propagation also. Yeah.
Thank you.
Okay, more questions?
First, thanks again for the presentation. That was very interesting. I'm curious about the wave propagation model calibration, specifically what parameters are being calibrated and if a calibration like that could address real-world features that might complicate this model, like weldments, rivets, cutouts, things like that.
Well, for the parameters that we are first estimating here, so these are parameters that are related to the material. So they are physical parameter. Like here, we are only estimating 3 parameters that are related to the propagation. And for the question related to whether or not this could be also used for estimating parameters that would be related to more complicated interactions, such as, for example, welds. I think that's also an interesting prospect. That's something that we should investigate. But like definitely with our experiments, we managed to show that when we calibrate some parameters, like based directly on the data, we can have very accurate results. So I think that's a nice idea. That's something we'll have to look more into in detail in the future.
Thank you. Just to clarify that, so this calibration is just related to sort of isotropic material properties? Yeah.
Yes, that's right. Also, here the calibration is still isotropic, but there are some papers that also integrate some parameters that are related to non-isotropic propagation. So maybe by adding more parameters, we will be able to have more accurate models. But yeah.
Cool. Thank you very much.
Okay, so Otmane, thanks very much. It was great. And now we switch to the next talk, which is Simon Birrell online. Okay.
Birrell.
Okay, perfect. Sorry, today.
Okay. No problem at all. Okay, let me know if you can see my screen.
Yeah. That's not your lab, right?
That's right, yeah. Yeah, it's a wet and cold day in the UK. I really wish I was in Malta. But okay, so I'm going to talk about simulation, learning and control methods to improve robotic vegetable harvesting. So this comes out of a project called VeggieBot that we've been working on in Cambridge for a while, which is a lettuce picking robot, a lettuce harvesting robot. It's sponsored by G Growers, which is a big business. It's the biggest grower of lettuces in Europe, based largely in the UK and Spain. And whenever you're doing a kind of business venture, the first thing you need to do is check out the competition. So I'm going to play you a little video of how lettuces are harvested now. So these are the human beings walking in front of a large mobile kind of lettuce factory. And you can see that they reach down, they pull a lettuce, they have a knife in their hands, they chop through the stalk of the lettuce, they pull off some of the outer leaves, they pop it into a plastic bag, they toss the bag into a carousel. And all of this with a cycle time of around 6 seconds, right? So this is pretty stiff competition. These guys do it really well. So the first thing is you're going to have to develop a robot out in the field. And this is definitely not your lab. This is a photograph of me out in the field with VeggieBot. I'm debugging. There's sun on my laptop, there's wind. Shortly after this photograph was taken, there was a thunderstorm. Rain started lashing down and there was thunder and lightning. And you can imagine what it's like to have thunder and lightning and you're in a flat field and there's a large metal robot beside you. But fortunately, we emerged unscathed. But one thing we really learned is it's vital to actually be in the field, rapidly iterating your prototypes and testing in reality. So here's a photograph. Here's a video of VeggieBot in operation. I'm going to take out my headphones so you can hear the audio. I want you to hear the wind. So let's just start the video. So it's a UR10 camera, UR10 robot arm with a custom end effector on the end. So it moves over, detects the lettuce, moves over the lettuce, comes down slowly. There's a soft gripper inside the end effector, which holds, kind of grasps the lettuce. Two pneumatic actuators drive a blade at the bottom of the cage through the stalk, pick it up, and then drop it. And this guy is one of G Growers' farmers. So he's doing some quality control. And pretty much it works. I'll plug back in. But notice the end. I don't know if you can see that the scaffolds with the overhead camera is moving in the wind. Everything is vibrating. There's a generator, which is also vibrating the platform. So these are rough conditions. So how do we stack up against the competition? So the human being requires no calibration and has a cycle time of picking of around 6 seconds. The robot requires continual recalibration because of all the vibrations, because of the wind, because of the platform getting knocked every time you move it. And it achieves a cycle time of 31 seconds. It's even worse than that because the human is also putting the lettuce into a plastic bag. They're taking the extra leaves off. So the human is doing more things than we are. That slowness, that 31 seconds, largely comes down to two factors. First of all, the end effector is very, very heavy. It's almost 10 kilograms. It's at the limit of what the arm can move. So the arm has to move slowly in order to avoid protective stop. So with a lighter end effector or a stronger arm, you could get around that. But in addition, it's slow because of the control methods, which is what I'm going to talk about now. It's interesting that talking to G growers, they've had a succession of researchers and startups bringing veggie, agri-tech robots to them. And the common problem they always have is that the robots fall to pieces or they don't work properly once they've been out in the field for half an hour or an hour. They just take too much punishment and get out of alignment, stop working. So the first method we used was open loop. So this is simply that we have a camera, we have the overhead camera on the scaffold we saw. We have bounding boxes for the lettuce with an object detector. And then we have a simple model of the platform. We know where the base of the robot arm is with respect to the camera. And we know more or less how high above the floor the platform is. So it shouldn't be too difficult, right? We just, simple geometry. We calculate where the lettuce is and we move the arm to it. So this is open loop. You figure out where you think the lettuce is, and then you just use inverse kinematics to move there. So this is a simulation. You can see it's pretty quick, assuming your end effector isn't too heavy. And here it is in the lab. We just move directly to the pre-grasp position, which is about 20 centimeters over the lettuce, and then we descend. So that should be fine. The problem is, as I said, every time you move the VeggieBot, you're not moving on a smooth lab floor. You're moving over kind of pock-marked mud. So everything moves, and the VeggieBot gets out of alignment, the camera shifts. And as I said, this is not kind of just a fault in the construction of the VeggieBot. It's, I think, intrinsic to Agritech. Okay, so what we did is we made a calibration system with a little Aruco code on the end effector. You can see it here. We move it to 3 different positions in the plane, and then we use linear interpolation to map any pixel on the visual viewport to a position in robot space. And it's actually quite difficult to move the Aruco code into 3 positions that are always in view. They keep getting occluded. But you had to recalibrate every time you moved the VeggieBot. So that wasn't any good. We then moved to a 2-stage servoing system where we use visual servoing. So we have a bounding box around the lettuce. We have a bounding box round the end effector, and we simply accelerate towards the center of the lettuce. And it's not one shot. We are continually updating and readjusting the position, the velocity of the end effector as we move. And once we get over the top of the lettuce, we're over the top of it in the viewport, but not in reality because of camera geometry. But at that point, we have a second camera inside the end effector, and the lettuce is pretty much in view at this position. And we can then just move the lettuce to the center of the viewport and then descend vertically. This is pretty robust. We don't have a model. You can bash the VeggieBot quite a bit, and it gets the lettuce. In fact, I mean, even if the lettuce had legs and was walking around, you could probably harvest it. But fortunately, that's not the case. So here we are. We see it in simulation. We'll see it in reality. And one thing you'll notice is it's rather slower than the open loop. And it's rate limited by the speed of updates from your object detector. In our case, with the onboard equipment, we had about 5 hertz. So 5 updates a second, and that limits how fast you can move the arm. Here we see it in, right, we can see the end effector camera, we can see the overhead camera. and it kind of moving the lettuce into position. So this works pretty well, but it's slow. So what we ended up trying was some system to get the best of the speed of open loop, to get the reliability of two-stage servoing, to make it more robust to equipment misalignment. And we call this open loop. So the way it works is, first we add some extra sensors. So we already have, with the Aruco board, we have the position of the arm of the end effector with respect to the camera. We add an Aruco board to the platform, so we know the position of the platform with respect to the overhead camera. And we add an IMU, so we've got the absolute rotation of the platform in the world. We then gather data. We look for successful picks, which we do with two-stage servoing. That becomes the training data. We have a very simple neural network with just two hidden layers. We have the positions I mentioned, the position of the end effector, the position of the platform, the rotation, we have the bounding box, and we map it to the target position in robot space of the lettuce. We then have the pre-grass position we can move to, and then we can use a little bit of visual servoing when we go down to kind of correct the final, any final inaccuracies. So as you can see, it moves very quickly to the pre-grass position and then slightly slower as it descends. And this was in part inspired by the human grasp, which, as you probably know, when you reach to grab something, there's a ballistic movement, which is very fast as you move your wrist close to the object. And then there's a more feedback-driven phase where you're actually moving the hand to grasp the object. So that's the learned open loop. In simulation, we took 2,000, a data set of 2,000, successful picks. When we tried it on the actual platform, we found that we could do it with 50. So it's quite a simple mapping that it's doing. You don't need a lot of training data. So this is the duration of the picks on the real robot. Open loop is fast, it's just under 5 seconds. Two-stage servoing is much slower, it's 9 seconds. And learned open loop is a compromise between the two. Next, we added perturbations to see the robustness. So in simulation, this is easy. We just had a kind of virtual ball joint underneath the scaffold, underneath the camera, underneath the arm to throw everything out of alignment. So we'll see that here. You get to see a lot of videos of lettuces being picked, but not as many as I've seen. For 6 months after the first veggie paper, I couldn't eat lettuce. Okay, so you see that the arm is out of alignment. We've added some kind of random noise there, but it still picks the lettuce. And when we tested this in reality, now this one we did test in the lab because when we were finishing the paper, it was outside lettuce growing season. So we couldn't go into the field and pick lettuces. So we jack up the veggie bot, we introduce noise under the camera and so on, and then we bring down and it picks. So as I said, the speed is a compromise between open loop and two-stage servoing. It's as accurate and robust as two-stage servoing up until quite high noise. I think you can see that with this last graph down here. So the conclusions are, the lab is not reality. If you're doing agri-tech, if you're doing field robotics, you've got to be in the field to really understand the problems. One of the principal problems we understood is agri-tech robots need to withstand a lot of punishment. And we think that learning to adapt is part of the solution. That's it. Thanks for listening.
Thank you very much. So we have time for 1 or 2 questions, either from here or from the remote participants. Okay, I have one. It might sound a bit strange, but any ideas about, let's say, using instead of one robotic arm, two arms, so that you can run a sort of operations concurrently?
Absolutely. It's a total waste to have a 6 degree of freedom arm doing this work. So I think the real innovation that we were trying to do here was the end effector and the software. right? The arm is a commodity. The main thing is to get the end effector down close to the lettuce, and then there's a whole hardware problem I haven't discussed, which is actually cutting the lettuce stalk. The way to do this, I think, in reality, would be to have some kind of Cartesian system on the front of that giant rig we saw before with the human beings walking in front of it. That advances very slowly over the fields. The way I would do it is have some kind of Cartesian system that had lots of buckets, like one for each row, or maybe several for each row, that can kind of adjust in the XYZ plane slightly. So that would definitely be a way of getting the cycle time up, right? So instead of 31 seconds, even if there's no efficiency gains, you double it, you get 15. If you have 4 of them, you're now competing with a human being. So absolutely, I think 6 degree of freedom arms is not the way to go with agritech, but we were really focused on, first of all, the harvesting problem, and then we were focused on the kind of unreliability of the model problem.
Thanks very much. And now I think that we need to switch to the next talk. So thank you very much. So now we switch to Christopher. And let me just switch. Okay. Perfect. Thanks very much. Oh, sorry, Mike.
Hey, all right. So I'm going to talk about incorporating noise into adaptive sampling. This was done by my lab, at USC, in the Robotic Embedded Systems lab, as a collaboration with the Karen lab, who does Protesian aquatic microbial ecology, which is basically studying algae in lakes for roboticists. So this smart autonomy that we use is adaptive sampling. In this work, I'm going to talk about using a robot that is a point-based sensor, gathering data like a chlorophyll sensor, salinity, temperature. I usually focus on marine robotics, but this can be kind of applied to anything that's gathering data like that. And if you buy these robots off the shelf, they perform these lawnmower patterns. So if you give it to a scientist, they basically say, here's a box, and the robot just goes back and forth in the box collecting this data. But many times you're in a situation where either you don't need all that data because you can use an approximate model and interpolate it. You want to do a study that you couldn't go back and forth that many times with the robot's battery capability. With like a drone, they only have 30 minutes. With even a robot in the ocean, that's 9 hours is not that long in the ocean. So you want to be able to do something where you can either cover more area or go to more areas. So that's where adaptive sampling comes in. The basic premise is that you create a model of the environment. You choose sampling locations which maximally improve that model, and then you update the model, and you sort of do that over and over again until you get a good model of the environment. You can see over here I've got a lawnmower path, and then compared to an adaptive sampling path that uses half the budget, you get sort of the same idea that there's a high concentration area there, and everywhere else is kind of a low concentration area. But a central assumption of a lot of these adaptive sampling planners and systems is that you exactly know where you took the sample from. And I'm going to use sample and data interchangeably, but sample means like one data point here. But we're in field robotics, we know that that never happens. I mean, if you have a GPS, you're pretty close, but in underwater robotics, you don't have a GPS. You rely on IMU integration, propeller counting, and so you get these noisy pose measurements, so you never actually know exactly where you took the sensing data from. And this is, again, really important in underwater robotics because at the surface, you have a GPS, and as you go farther down, your uncertainty propagates, and you're relying on IMU integration, so you get sort of heteroscedastic noise. This can also happen if you're doing like indoor SLAM with no GPS, where you maybe are in a hallway, now your measurement noise is worse because you have an unobservability in one one direction. So why do this? It's important for single robot sensing because you have this heteroscedastic noise where you have uncertainty in different, higher uncertainty in different areas. But it becomes really important if you're trying to merge different kinds of robot surveys together. And sort of a dream that I have for like a single person deployable system is that you fly a drone over the lake you give that data to an underwater robot, and the underwater robot can make a more informed decision of where to sample. Underwater robots tend to be much slower than drones, but in this situation, the drone is going to have pretty good localization because it has a GPS on it. The underwater robot's going to have worse localization, and so you need to be able to merge those data sets together and in a reliable way where you incorporate the localization and certainty from each robot in different ways. So to model the environment, the standard in adaptive sampling is a thing called a Gaussian process. Basically, the idea is that it's non-parametric, so it takes all the samples that you have. It's continuous, so it's defined over any continuous area. And it has uncertainty quantification, which is the most important thing for adaptive sampling, really. I'm not going to go into the math of it too much. The most important thing is I have a Gaussian process over here that I've conditioned on 0, 0, 1, 1, and 2, 3. You can see it kind of gets more high value in the mean, which is like the sort of predicted value of the model. And in the variance, as you get closer to the points that I say I've sampled from, the variance goes down, and you get farther away, the variance goes up. So that gives you an idea of how to do this adaptive sampling problem, because now you can quantify how uncertain your model is. These Gaussian processes do not work really well for distributions, and so when you have a state estimator, you have a distribution over your poses and not a single pose. So in order to deal with that, we do a Monte Carlo approximation. Some people from economics who are smarter than me already came up with kind of how to do this. So basically, sample from that distribution D, which we do get sampled actual poses of the robot, which I'm going to call X. And then for the mean, you just take the expected value of the mean from the Gaussian process of all the poses that you drew. And then for the variance, you take the expected value of the variance plus the variance of the mean. And this is where you get the idea that you should sample more samples from areas which you are less certain about your localization and less samples from areas that you're more certain about your localization. But so you need to balance off this trade-off between spatial coverage and coverage of places that you're uncertain about your localization. We extend this in two ways. The first is that we add like a weighting system where we can weight the samples by the probability that you would observe them in two different ways, and I'll talk about that in a second. And then we draw the sampled points from the distribution at every step, and then we also incorporate it into a planner. And this is really, in my opinion, nice because all you need for this to work is that you can sample from a distribution. So over poses, so you can do it for like particle filters, Kalman filters, information filters, pose graphs, whatever you can derive a distribution that you can sample from. So this is the basic algorithm for the modeling step. At the first part, you draw samples from your previous pose distributions. You then calculate this likelihood. This is really just used as more of a weighting. It's not exactly like a probability likelihood, but the basic idea is that you have this part, which is the probability of drawing that sample from the state distribution. So this is maximally if it's the mean of like a normal distribution. And this part is the probability of observing this value given the Gaussian process that you built of the sampled values. So this is like, given the other points that I've sampled, is it likely that this point will have that measurement? And so that gives you a weighting thing. Then you draw samples from the query distribution, which is like the next point I want to go to. And then you build up a Gaussian process from the ones that you've already sampled from your previous distributions, the values that you measured there, and then you query it for that, the sample that you drew from your query distribution, and then you just calculate the statistics that you need to tell you things about that point that you're curious about, or sorry, the distribution that you're curious about. So here's a comparison of the modeling techniques. This bottom part, so basically the way this works is you have a Gaussian process which is given points and compared to a noise-free, like all the noise-free points. And they're given noisy points except for this one, which is given the noise-free points. And this is the amount of samples that you give the Gaussian process. So you can see that this is like if you were not giving noisy points, how well would you be doing? This pink line is, if you're giving these noisy points, but you don't do any noise compensation. You just sort of integrate them blindly, which is actually what we're doing most of the time in adaptive sampling. And then all of these methods are the methods that we sort of proposed in the paper. It turns out if you use that weighting system, it works a little bit better. It's hard to see in this, but if you're curious, you can see that in the paper. And then to extend this to planning, we need to integrate this into a planner. There's this planner called RIG Tree, which the short thing about it is that it's RRT, but it can do information gathering. And so the thing that we modify is that you have to put the data submitter parameters in the node as well as the other stuff you need for RIG Tree. And you use this objective function for planning, which is just the entropy of a Gaussian process, but instead of taking it at a single point, you use this expected variance that I showed earlier from the Monte Carlo modeling technique, and you get this expected entropy objective. This is sort of shows what it looks like, where the farther you get away from the starting point, the more information that you gather, and this depends a little bit on, again, the localization uncertainty that you predict when you get there. So I'm going to discuss a little bit about the field data that I'm going to use as the data set for this. We went to Clear Lake, California, which is a Superfund site in Northern California. This is actually what the water looks like from a visible light camera. It's very gross. And it's also, unfortunately, the drinking water for a lot of people. So we use a DJI Matrice 200 drone with a Centera quad hyperspectral sensor. If you're interested, I can talk about the spectrum that we used. But so we collected multiple day data. We wanted to go longer than we did, but we were cut short by COVID. And then YSI brought an EcoMapper, and they operated this vehicle. And we also did physical sampling. The YSI has published a white paper on the EcoMapper, and then there's more discrete sampling papers if you're curious about how that part worked. And I think that some of these data sets appear in that paper as well. So these are what the data sets look like. You can see that they're basically red and yellow where there's gross algae mats, and you can physically see those on top of the water, which makes this a good data set, in my opinion, because you can verify that the camera is seeing a more interesting view of what you can see with your eyes. We use a 710 nanometer band. I can talk about why afterwards, but so we did 2 experiments using these data sets. The first is this thing where I said maybe you use a drone as a pilot survey, and then you want to plan on top of that for a robot. Basically, we localize the drone with a pose graph, and then use the resulting distributions over the beliefs for that. So this blue line is basically a traditional adaptive sampling scheme where you just take the points in, and then you use RRIG tree and plan from that, and you don't do any noise compensation. The orange line is you just use a traditional adaptive sampling planner, RIG tree, but then when you come to model it, which is when you would give the data set to the scientists, you actually use our Monte Carlo estimation technique. And then the green line is you use the full sort of paper technique where you use Monte Carlo sampling for the modeling and for the planning. As you can see that so this reinforces the idea that if you take more samples from where you're more uncertain, you get a better estimate when you use this Monte Carlo sampling, because the green line, which does both of those things, outperforms the blue line, which is a baseline, and outperforms just using it at modeling time. But you can actually get pretty good advances just using this at modeling time. If you have a resource-limited robot where you don't want to do this Monte Carlo sampling on it. And then this experiment is like a textbook particle filter experiment where you have 10 landmarks that you know the location of, and at each step you get noisy range measurements from them. So this is maybe if you have an underwater vehicle and you have long baseline measurements to a buoy or something, but you don't exactly know the angle to the buoy. So this is where you get kind of a weird particle filter distribution where it becomes very non-Gaussian. You could get multimodal beliefs if you get a bad particle filter state and stuff. So you can see that it's very hard for the baseline to do anything here because it has a lot of uncertainty about its own pose and in a weird non-Gaussian way. So the Gaussian process doesn't sort of naturally handle that very well. And then our modeling technique and our planning technique do really well here and allow you to actually learn in this kind of complicated environment where you never really know exactly where the sensor that you're taking data is from. And the belief distribution is really non-Gaussian. So In conclusion, we propose a novel way to do adaptive sampling when you have localization uncertainty, which is, I think, a fairly realistic problem, especially in the lakes that we work in, where the uncertainty relative to the size of the lake is pretty large. And we're using a Monte Carlo estimation technique from the police distribution over robot states. The Monte Carlo estimate improves modeling error, and that's the pretty easy way to apply this. It doesn't really, because you're going to do this on your laptop or computer afterwards. We also can use it to improve the objective for planning, especially when you have a lot of uncertainty and a lot of kind of weird uncertainty on your belief distribution. And then one thing that I want to take away is that noise on the pose observations can cause your adaptive sampling routine to not work very well. And if you're not cognizant of this, because you have the state estimator and the planner sort of totally separate, you won't actually realize that this is happening because you'll just ignore it and you'll just assume that you have a good estimate of your actual pose when you may not. And then again, it allows you to integrate with prior surveys taken on different robots or satellites in different scales of operation and uncertainty. That's pretty much everything I have. This is my contact. If you're on Twitter, follow me on Twitter. Thanks, everyone.
Thank you very much. So we have time for 1.5 question. Okay, there's one there, so then we'll have half question.
So thank you for the great talk, very interesting topic also. In the last slide that you've used, there were these 4 environments. Yeah, and I wonder what happened in the 4th environment, because the baseline method seems to be quite good there. What happened there? What did the environment look like? And
Yes, so that's this D environment, and our sort of theory as to why is because you can see there's many fewer algae mats, and we think that none of the methods actually found this algae mat because sometimes they only explore this area, and so it has a very low data range. So being off on your localization there doesn't actually matter, because you can imagine if it's all the same value here, if I think I'm here or here, it doesn't actually matter for what the resulting map looks like. So that is another thing to be considerate of these happen to be data sets, obviously I chose these for a reason, happen to be data sets where if you're off by where you think you are by a little bit, you get a really bad estimate of what the actual concentrations are. And this actually tends to be true for most algae distributions. It's just the day that we were there, actually I think the wind shifted the other way, so the algae got blown the other way in that lake.
okay, thank you.
Okay, thanks very much. So I think that we should stop here. I have more questions, but then we can handle those offline. So thank you very much. So, and next talk will be delivered by Monica. So, Monica, are you around?
I think she was connected. I saw her. Yeah, she's here.
Okay, there she is.
Fantastic.
Yes, can you hear me?
Yes, we see and we hear you. So share your screen anytime you wish. Perfect, yes. Great, terrific. Go ahead. Just put it in the presentation mode. Okay. Floor is yours.
Thank you. Hi, my name is Monica Rosnier, and I'll present an experimental analysis towards high water quality monitoring with robots. This work has been done in collaboration with limnologists. So aquatic monitoring is important to provide data which can inform protection of and management of good water quality for drinking or recreation. However, the limited spatial and temporal coverage of traditional limnological monitoring may constrain inferences about water quality. For example, monitoring typically involves measuring different parameters at weekly or monthly intervals at a single site. Although continuous sensor measurements on fixed location buoys has increased temporal sampling frequency, the number and type of such sensors in a lake are typically limited by cost constraints, thus limiting spatial coverage. A limnology computer science interdisciplinary approach of designing sampling strategies within robot-based limitations is a promising method to monitor water bodies more effectively. We are specifically interested in how robotic coverage patterns or strategies may impact water quality parameter measurements and how it might affect our understanding of horizontal heterogeneity in biological and chemical data across lake surface. So recent biology-based research projects are still mainly based on analysis from very few number of stationary buoys on a lake, thus limiting the spatial coverage inferences and knowledge. So moreover, buoy and sensor locations are often selected based on discretized zones, such as open water or above or below thermocline. But heterogeneity within commonly accepted lake zones is increasingly being recognized as critical for understanding lake ecosystem functioning. So there's a lot of importance to monitor these key factors that drive quality by collecting and integrating higher spatial and temporal resolution data using autonomous vehicles. Robots work that could be applicable for water quality monitoring can be identified in two types of approaches: complete coverage and adaptive sampling. Complete coverage is great for collecting high resolution water quality data, but typically takes a long time and can be more delayed due to slow response time of an optical sensor like dissolved oxygen probe. Adaptive sampling can process real-time sensor data strategically, but many of these works do not use slow response time optical sensors, again, like the dissolved oxygen probe. So these prior studies highlight that research is needed to better understand how robot movement may interact with sensor characteristics to impact data quality and bridge the gap for implementing effective and reliable sampling methods in real-world environments. Thus, we address the following questions. How do robotic motions affect water quality sensor response time? How do water quality measurements compare between robots and fixed location buoys? How can robotic coverage paths best complement and extend monitoring data from discrete water samples like chlorophyll A concentrations? Our main push here is to provide insights that will improve robotic planning techniques for sampling reliable sensor data, thereby providing higher resolution temporal and spatial information about water quality. Here's a system of robots and buoys that were used for water quality collection. The autonomous service vehicle we call Catabot is equipped with a sonar, cameras, and a GPS. The underwater ROV is equipped with a sonar and a camera. Both are equipped with WiSi XO2 sondes, recording different water quality parameters, but most notably water temperature, dissolved oxygen, and chlorophyll fluorescence. The sonde on the ROV also has a turbidity sensor. The ASV does not, though. There were two buoys at the lake we were conducting our experiments at that measured DO and temperature at various depths. We also hand collected water samples that were analyzed for chlorophyll A afterwards. So we conducted experiments at the lake from ice out in April until September 2020. During these expeditions, the ROV collected samples at a winter buoy shown in the previous figure that were fixed with temperature subsensors every half a meter to a meter down, as well as a DO sensor at the top and bottom. The ASV sampled near a summer buoy that collected DO at temperature 1 meter below the surface. We also collected hand samples at the summer buoy and at home base. In addition, we evaluated the effect of sensor response time and field conditions on data quality. We used the ROV to test equilibrium time for temperature and DO across depth. For the ASV, we analyzed sensor response time and instability by internal factors, so by different robot-induced motions, and by external factors when it encountered adversarial environmental conditions. Finally, we determined how different ASV coverage paths from the adequacy of sampling spatial resolution relative to spatial variability and water quality variables within the environment. At the lab, we conducted controlled scenarios such as hot, cold water and still or bubble water to record sensor response times. They were averaged out to be about 20 seconds for temperature and 27 seconds for DO. However, the proportional temperature differential was greater than that for DO, suggesting that DO readings take slightly longer time to stabilize for a given differential. This is expected for optical-based sensors like the DO. To compare these response times to those in real environmental conditions, the ROV collected data as it moved up vertically along the buoy line, and it stayed at each depth associated with the sensor on the buoy for 1 minute. In these profiles, temperature and DO measurements from the ROV sensors stabilized after about 10 to 15 seconds. Each sensor's response time is not only based on the type of sensor it is, but also the current variability of the environment. For example, the onset of thermal stratification by May 17th meant that both temperature and DO now changed with depth. In comparison with the nearly isothermal conditions in previous weeks, the ROV control would need to actively be aware of how readings change with the given depth and pause longer at specific depths when needed. For the ASV, two main factors affected sensor stability during a path coverage: motion attributes, internal, and environmental conditions, external. First, rotational and translational movement at each waypoint may delay sensor responses. For example, to monitor the sensor reading stability, the ASV arrived at home location at 82 seconds and stayed in place at 95 seconds to monitor sensor reading stability. The DO sensor reading stabilized after approximately 30 seconds, indicating that the previous motion of the ASV impacted sensor readings. Second, environmental conditions independent of ASV movement can alter the ASV path, which may also affect sensor reliability. When the ASV adjusted its heading to counteract external forces in the red shaded area, the motions cause higher variability in DO measurements. However, these fluctuations were relatively small and likely not biologically meaningful. Though high variability in sound readings for future deployments may be a useful indicator of potential sensitivity to robot behavior. In other situations, sensor data reliability was more prominently impacted by unintentional interactions with the environment. For example, the ROV hit the bottom of the lake and stirred up sediment. This led to misleading water quality readings, including an increase in turbidity followed by a decrease in DO. That was simply a result of the unintentional interaction with the sediment. In this case, it was important to have the turbidity sensor paired with the DO sensor so the cause of the inadvertent sudden drop in DO could be easily identified. The faster response time of the turbidity sensor compared to the DO sensor could predict incoming reading changes for DO or other water quality measurements. A little jump back to the ROV sampling. The ROV sampling along the winter buoy line improved vertical underwater depth resolution, while the higher frequency data from the SON increased the temporal resolution beyond that of the 10-minute recording interval of the fixed buoy. ROV and winter buoy temperature measurements generally agreed. On May 17th, the SON on the ROV produced more variable readings at most depths, possibly due to the greater difference between surface and bottom temperatures. A comparison of DO concentrations were also quite similar. The observed discrepancies are within the measurement error. While the differences in sensor response times need to be resolved, ROV with the SON greatly increased the vertical resolution of DO data. In fact, the higher resolution ROV data revealed the development of an oxygen bulge in the middle of the water column on May 17th. A different spatial coverage paths performed in a single water body demonstrated horizontal variability in chlorophyll during short-term deployments. Although cyanobacterial bloom did not occur in the lake during the expeditions, the coverage methods can help understand the patterns of phytoplankton distribution. A spatial pattern in chlorophyll fluorescence was more visible from the first path coverage scenario, possibly because that was the first path attempted on this date. However, mean chlorophyll fluorescence was very similar across all three coverage paths. AC deployments may also enhance understanding of this relationship between daily environmental conditions, such as wind and water currents, and within lake chlorophyll patterns. The line artifacts perpendicular to the trajectories of the paths could have been from wind or water currents, which usually follow the southeast direction development of windrows. Our experiments confirmed that robotic water quality measurements are fairly robust to sensor response times and robotic motions, though there are a few situations that might impact biological interpretations. In particular, varied sensor response times, unintentional robot environmental interactions, and ground truthing need to be considered when designing sampling strategies and in post-sampling data quality control measures. So based on our results today, we offer the following guidelines for operating robotic water quality sampling strategies. A robot should stop or reduce speed to provide sufficient time for different sensors to collect accurate readings, especially optical sensors. Allow the robot to self-adjust waiting times for sensor equilibration, similar to adaptive sampling routines. The robot should consider factors such as environmental interactions and external forces and minimize their effects when possible. Robot collected data should be validated with other data streams when possible. And when robotic movements that may affect sensor reliability cannot be avoided, a post-sampling data quality control protocol should be developed specific to the robot instrumentation and environmental conditions. The results show that the ROV and ASV sampling, when performed with robust validation and quality assurance and quality control measures, can lead to the collection of high quality, spatially and temporally resolved water quality data. These data are necessary for characterization of whole lake water quality, identification of hotspots of concern, and ultimately our prediction of water quality. Our next steps is to conduct extensive tests on different ASV coverage paths during a period of decreased water quality, such as a bloom, to have a thorough understanding of the balance between high resolution spatial heterogeneity and deployment time. In addition, we will expand our investigation on how to determine, with and without a turbidity sensor, if potential disturbances in the environment cause significant fluctuations in the sound readings. We also aim to extend the system to multiple ROVs and ASVs with a strategic motion planning methodology that is self-aware of sensor characteristics and all the impacts from motion attributes. A well-informed system of robots combined with data collected from existing monitoring efforts can help create a more holistic picture of spatial and temporal variability within a lake and provide limnologists and lake managers with better data and tools for understanding and predicting changes in water quality. Thank you. And if you have any questions, feel free to ask them now or email us.
Thank you very much. Then again, we have time for a couple of questions. Okay, there's one there.
Hi, thank you. Great talk. I was wondering for the equilibrium time for different sensors, did it appear to depend on like depth location, or is it just on the water temperature?
So water temperature will technically, based off what I've known from working with all the different limnologists, is that you would expect that the temperature will never change more than, what was it they say? I had it written down, about like 5 degrees within like a few degrees between like a half a meter. However, dissolved oxygen will change pretty drastically, especially during thermal stratification. So such changes in depth will be very sudden. So if you are a diver and you see those like the thermal stratification, that haze, that is very sudden.
Thank you.
Okay, are there more questions? Okay, so if that's not the case, then thanks very much. And we will switch to the last but not least presentation, which will be done by Stuart Eifert. I hope I got the pronunciation right.
That is correct.
Thanks very much.
Sorry for missing my scheduled time.
It's okay.
Cool. Let me just share my screen. Okay, is that showing up fine on your end? Hello? Hello, can you hear me?
Yeah, we can hear you, but can you put in the projection mode?
Oh, sorry, it's not showing up
Not
for
yet.
you. Yep.
That's it. PhD thesis. Okay.
Okay, now it's...
Here we are. Perfect.
Okay, great.
Okay, floor is
hi,
yours.
thanks. My name's Stuart Eifert, and I'll be presenting today on behalf of myself, Nathan, Hare, Navid, and Salah. We're from the University of Sydney in the Australian Centre for Field Robotics. And our work today is experimental evaluation of a hierarchical operating framework for ground robots in agriculture. So I'll begin by explaining exactly what that means. So our work is about overcoming challenges that exist in order to achieve long-term autonomy in unstructured environments, specifically in large-scale farming around livestock. So a couple of the main challenges that do exist that we address in our work are resource considerations, looking at the onboard limitations, so the onboard resource limitations available to a robot operating in real-world environments, and how that's impacted by the efficiency of its long-term plans. Additionally, we investigate how that interacts with agent interactions. So when a robot is operating in real-world environments in either crowds or herds, how it might have dynamic online plans to lead to collision avoidance might directly impact its resource usage. And so this work investigates how a framework can be developed to combine the long-term efficiency with short-term collision avoidance in an overall approach that allows for extended autonomy. So the main contributions of our work are the validation and evaluation of this framework, which we've developed in our prior work for long-term and robust deployment, a demonstration of this in a real-world test for energy-efficient navigation in the presence of moving individuals, and a demonstration of this for the specific task of weed spraying in a dynamic farm environment. That's the robot we used for all the trials used in this paper. So I'll just begin with some brief background about what approach we use for long-term planning. So it's built off some previous work that Nathan had developed, where assuming that a robot has been given a previously mapped environment and a set of waypoints, it will develop the probabilistic roadmap between all nodes, and using a traveling salesman approach, it will find the energy efficient path between them. So linking that in with our dynamic path planning, which I developed myself in prior work for this work, the dynamic path planner itself is built upon a recurrent neural network motion model of agents, which take as input the robot's action in order to learn a response model. So in this way, we can develop a state transition function type approach where, given an agent's possible future action and the state of agents, so given the robot's possible future action and the state of agents around it, we can predict the likely next future state of a crowd or a herd. So we use this in a Monte Carlo tree search style planner in order to develop a dynamic plan that allows for consideration of response of agents nearby it. So we have, in our prior work, developed a hierarchical framework for this task, and we've tested it in a simulated environment. This framework has combined our long-term planner with the local dynamic planner that I just discussed, and the simulated environment involve the use of pedestrian motion models based on optimal reciprocal collision avoidance due to the non-availability of livestock motion models yet. And the tasks involved being supplied with a series of waypoints and traversing these whilst following an offline computed optimal path shown in yellow currently, and generating local updates to that using the local dynamic planner in order to reach the required positional accuracy at each waypoint. In the experiment that we conduct in this work, we aim to replicate this task in the real world for the task of weeding pasture in agriculture. So the approach specifically makes use of, as inputs, RGB and LiDAR for perception, conducting the object detection and tracking, which is fed into both the dynamic planner and a fail-safe collision avoidance module. In our previous work in simulation, we have run this framework. We've tested this framework using both the Monte Carlo tree search generative RNN that I discussed previously, as well as comparing its use just when the fail-safe collision avoidance module is used, and when the local dynamic planner is switched out for a simpler potential field planner, and when it's switched out for a state-of-the-art reinforcement learning planner that also considers responses of nearby agents. The long-term planner used in all of these was the discussed probabilistic roadmap planner. Additionally, there is a hierarchical mode controller that sits above these planners and decides when to listen to the local dynamic planner to make adjustments in order to follow the long-term planner, or when to just enable the fail-safe collision avoidance module. So I'll get onto the actual experiment that our work focuses on. So it's conducted in the Arthursley Farm, which is just outside of Sydney. It's about 2 hectares in size. The robot is given a start position that corresponds to a charging station. That isn't included in this work, sorry. It's planned for future work. It's supplied externally with a set of waypoints from previously mapped weeds. And then it initially has to plan a resource-efficient path over the undulating terrain in order to meet all of the weeds, given its limited onboard resources. And then whilst conducting that plan in real time, it has to navigate around the presence of dynamic agents. We again replicate the agents just using pedestrians, so humans, rather than livestock, as we do not have yet a livestock motion model due to limitations with perception. We've found in the past that predicting livestock motion is heavily reliant on predicting the pose and orientation of the animal itself, and we haven't, as of yet, been able to do that accurately enough in order to develop a livestock motion model that is more accurate than just constant velocity model. So additionally, during this task, the robot is required to avoid unmapped static obstacles. And then when it does get to each waypoint, it needs to reach the positional requirement needed to actually spray the weed. For all experiments in this work, we use the Monte Carlo tree search method that I demonstrated earlier. I'm now going to switch to a video. So please let me know if this works on your end. Can you now see the video playing? Is that a yes, sorry?
Not sure about the video, but we can see the map. Okay. Now,
oh, okay.
Yeah, okay, got it.
You can see the video?
Yep.
Okay, great. I'll just briefly pause it to talk you through what is happening. So this is a video of the extended navigation trial. In the top right corner, you can see a map which is being drawn as the robot traces out the dark blue reference path. The robot is shown tracing it out in light blue when it's in its long-term mode. And when it detects agents, which are shown on the map in light green, it enters dynamic mode. Each time it returns to the base, which here is just simulated, there is no actual recharging station. Again, future work, sorry. The robot is supplied with a new set of waypoints and computes a new energy optimal path. So the point of this experiment is primarily to determine whether the real world results of conducting our framework, where we are combining the dynamic path planner with the long-term reference planner, do match what we found in simulation. And I'll talk through those results after the video completes. But it is worth noting here that there are significant spurious perception errors you can see, but the majority of these are handled by the planner approach correctly, and when they aren't handled correctly, leading to the dynamic mode being implemented when it doesn't necessarily need to, the planner does return to the long-term mode, and we can quantify the energy lost during these and compare it to what would happen if different planning methods were in use. So here's an example taken from a drone of one interaction. So you can actually see the dynamic planner at work. So the robot gets into the clear and returns to the long-term path. Additionally, we in fact have conducted further experiments of this framework in denser crowds, but those results I won't be showing today. Sorry. Okay. All right, back to results. So hopefully on screen for you now, you're seeing 4 images which show an example interaction with pedestrians. So this is just breaking down exactly what is happening in the dynamic path planner approach to give you an idea of how the robot does search across its action space whilst considering each agent's response. In this example, the Monte Carlo tree search space is shown in light green in the top, whilst the agent response is the actual heat map with time steps numbered. The bottom shows the main picture as time 0 with 2 additional time steps at 1 and 2, which highlight how the robot's perception limitations enable it not to see the distant pedestrians, but it is able to react to them when it does see them. So, sorry, this is actually a results page. Sorry, not next steps page. So this is, yeah, I'll just jump past it. Sorry. So in the results page, we compare the energy efficiency and navigation time efficiency of our approach, which in these graphs is the red column versus the simulated works from our prior work. So we can see that the energy efficiency of ours in red, which we expect to match the black column, that's the simulated approach using the Monte Carlo tree search, does begin comparably and doesn't grow nearly as much as the fail-safe method, which is the green one, but does grow significantly more than we had expected it to, which is highlighting the difference between the simulated and real-world implementations. Similarly, in the navigation time efficiency, we expect the navigation time to stay higher for our real-world experiment, but it does diminish, again, highlighting the differences between the simulated and real-world. But we are able to show that we don't diminish nearly as much as using a fail-safe method, which has been used up until now on our robot for real-world deployments. Another important result is that the deviation from the optimal path is significantly less with the failsafe, as you would expect, but it is also the highest using the more responsive Monte Carlo tree search and the reinforcement learning in the light blue and the black and the dark blue in the columns. Our real world shows comparable high deviation from the optimal path, but whilst using a simpler method, the potential field can decrease this. That links into the future work of online adaptive framework. Whilst using, for instance, a simpler potential field method can allow less deviation in very undulating terrain that can be significantly impactful on energy usage. And so the development of an adaptive framework that allows changing between simpler dynamic planners when in less structured or more difficult terrain is something that we should consider in future. Additionally, a consideration of offline crowd density to allow the offline planner to take into account where areas that might have greater crowds and avoid them to begin with is something that we will be working on, as well as improving the livestock perception model so we can do real world testing with livestock. Thank you.
So we just have time for a quick question.
Yeah, there is one from distance.
Perfect.
Marcelo, is it you? Just can someone please unmute Marcelo Ang? Okay, you can speak up.
No,
Marcelo.
I was just clapping. It's not a question.
Okay, clapping. Okay.
It's a perfect question. Thank you, Marcelo.
That's good. That's good.
Thank you.
Any questions from the room? Okay, I would like to ask Stuart to stay connected along with Rohan and Monica and Simon. And then I'd like to ask the two presenters to come up on stage and leave the words to Joao for the moderation of the discussion.
Okay, so thanks very much. I think this was a great session, and because we're talking about field robotics, I would like to share, let's say, some thoughts and say, kind of ask at least two questions. The first one has to do with the thing that one of the difficulties of field robotics is to go from the lab into the real world. And do you have any kind of insights on how to speed up that kind of development process and make it easier? Because it's not that easy.
Yeah. One problem we run into as a smaller team is that we don't have any technicians, which makes it very difficult. But I think from larger teams, and I've worked with like JPL, who go from lab to the field pretty quickly, is that you really need to have good operations, which I think as like robotics PhD students, we don't really like consider that often, but like operating procedures and standard techniques for how to deploy your systems is like, I think, so important. And I think that's what like larger teams do well. And I think that's actually something that some people talked about the ZepG challenge. That was like one big challenge, I think, for a lot of the teams there, was developing not just these incredible technical systems, but incredible like operating systems of deploying them and figuring out how to get multiple robots deployed efficiently, which is just always a challenge. And I think one thing I've been joking with my colleagues about recently is that like, well, we can save you time with adaptive sampling in the actual sampling routine, but if we take an hour more and only save you if we take an hour more to deploy the system because it's so complicated to deploy and you have to choose all these parameters, and we only save you 30 minutes of sampling time, we'd like cost you more time than we've saved, and we might as well just run the robot for longer.
Perfect. Thanks very much. Otmani, any comments on this?
Yes. So I think like going from the lab to the field is quite a challenging step, like in my situation. So I'm kind of still stuck in the lab. I've not yet like tried the algorithm on a real structure, but I think that maybe we can think about like strategies to speed up this like how to have algorithm that can be that can work on the field. I think like we are kind of thinking about strategies, and some of the strategies may be related to like the robustness of the algorithm, and I think that if we already consider like robustness criterion in lab environments, if we include this like this criteria like in the testing process in the labs, I think that can help. But of course, this won't like replace this won't replace like the techniques that we would design directly based on the results we would have acquired with data that are acquired on the field. Yeah.
Okay, thanks very much. Now I'll switch to Rohan. Have any comments on this?
Yes, can you hear me?
Yeah.
Yeah. So my main sort of like comment would be, to kind of have very fast build, test, and fix cycles. So one of the sort of like habits that many PhD students have is to spend a lot of time on doing like literature search, find some novel idea, implement it for like 6 months, and then go into the field. And you kind of like discover that, hey, the real problem actually lies somewhere else, and you've been working on the wrong problem. So our strategy in SubT was what we call like fail fast. And the secret was to, build an end-to-end working system that's very simple, deploy it in the field, and start figuring out where the real bottlenecks are. And those bottlenecks actually led to, interesting research ideas and many papers in the future. And they also had a huge impact on the performance of our system at the same time. The other sort of detail I would add for good field operations is we almost had a setup like mission control where we had like dedicated roles, including including roles like note taker as well. And we also had like good checklists for the robots. And the idea is that every time you go in the field, you'll discover something that you should have planned earlier. So having a checklist that you can improve on after every field test really helps.
Perfect. Thanks very much. So Simon, any insights into?
Yeah, I concur with Rowan that the best thing is to get out into the field as early as possible and iterate as quickly as possible. It might be helpful, actually. I'll just very quickly show you a few photographs of the, so how the VeggieBot started. So we didn't start off with a platform like that. We started off with these crazy experiments, like taking a Baxter. You see my screen? We took a Baxter out into the field. And then, we also tried multiple iterations, different types of lettuce picking devices. So here we've got a rotary electric motor with a blade that goes around and kind of chops the lettuce off. You can see all the PhD students out in the field just trying all these different, very unpolished systems. We call our end effector a bucket because it actually started as a physical bucket, right? So that would be my main advice, is just get out in the field as quickly as possible, do as little as possible in the lab, and just try lots of things and discover the problems.
Perfect. Thanks very much. Monica?
Yes, I think our lab's approach is a little different from like how to get into the field, is more of actually finding collaborators and the community, like talking to the community. So where we do sampling is actually been associated with retired people who live at the lake and are so happy to help and improve like the environment there, and they let us use their boathouse. So all of our equipment is technically there except for the main robotic electronic stuff. So we are able to assemble everything in like 15 minutes pretty quickly, like pump up all the catabots. Even with collaborators and out of state, so there were times we would once a week drive 8 hours one day just to sample at a few lakes. And this year we decided to build a new boat and teach it to undergraduates at different schools for them to actually deploy it for us and to also like use it for their own experiments. So I think collaborations is really key if you want to kind of like connect to other people, get the community excited and more knowledgeable in what's happening in research, but also improves your own side too.
Perfect. Thanks very much. Stuart, any quick or succinct comments?
Yeah, I'll sum it up by saying I definitely agree with Rohan again that failing fast is really necessary. I'll maybe add one additional point that during COVID, the limitations on us actually accessing field work really helped innovate the development of a good simulator, which we found is no replacement for field testing, but has now enabled us to fix a lot of system-based problems that we would have otherwise not been finding until we got into the field, and can really chew through a lot of time.
Okay, perfect. Thanks very much. I don't think that we have time for another round of questions, but I would like to make one quick comment.
Marcelo probably has a comment this time, I believe.
Yes, very quickly. If time permits, just a comment and question to everybody. Every time we see a task the robot is doing, especially to Simon's talk, where the competition is very stiff, right, for the lettuce, and robot is just so slow in doing it. What can we all do to make the robots at least approach human capabilities in picking lettuce, for example? Thank you.
So one of the things I alluded to in, I think the question at the end of my talk was, you can parallelize, right? So even if your main task is slower than the human, you can stack up you can do multiple of them in parallel. So that way you can always kind of beat the human. In our case, the slowness was not really, that's not the problem we were trying to solve. The hard problem was actually picking the lettuce. That had been tried many times before and it had never been done. So we were focused on that problem. The problem of speeding it up is partly through control methods, as I said, partly through parallelization and just engineering to make the end effector lighter.
And also maybe the quality of less damage to the lettuce, maybe. I don't know.
Exactly. I mean, so with harvesting robots, there's a well-defined series of metrics that you can use in terms of damage, the success of picking, success of detecting, the damage, and so on. So yeah, there's a well-defined series of metrics for all of that.
Okay, thank you.
Okay, thanks very much. Do you want to say
Can I do a quick
something?
question? I think for compared to human baselines, it's also in some things like where Monica and Joam and I work, it's easy because the human baseline is drowning. So sometimes it's easy to find. It's not easy to find a human baseline there, but it's easy to beat a human baseline because there's no human baseline. So that's something we can consider in field work too, is trying to find solutions like that.
Okay, perfect. Thanks very much. I just have one quick comment to basically summarize this, which is, so right now I'm coordinating this U project about marine robots. And this is what is called an infrastructure project in which we are supposed to provide access for free to our toys. And this means that people from all over the world can apply to use our AUVs. And actually we got something like 50 successful applications from all over the world that had access to our assets. And that really makes a huge difference because let's say they don't need to worry about the specifics of the operation. If they have some nice algorithm, okay, just run this algorithm on our assets. And not only on AUVs, ASVs, ROVs, but also access to ships. And I think this is an interesting way of bridging this gap. Okay, so this was a great session. I wish we could continue, but I'm pretty sure that Bruno won't be happy with that. Same thing with Osama. So I guess that we should close here. And thanks very much.
Okay, coffee break now, and we will start at 11:10. Okay?
Talk about life since then. Talk about